Here is a 5 by 5 matrix. Its eigenvalues live somewhere in the complex plane, and if you wanted them, you might reach for a characteristic polynomial, or a numerical solver, or an afternoon. But give me 10 seconds, one disk per row. Every eigenvalue, without exception, sits inside the union of those disks. You never had to solve anything. The rule that catches those eigenvalues is simple. Pick any row of the matrix. The diagonal entry on that row is the center of a disk. The radius is the sum of the absolute values of the other entries in that same row. Draw the disk in the complex plane. Now do this for every row. You get n disks. Gershgorin's theorem says every eigenvalue of the matrix lies inside the union of those disks. Not most of them, every single one, no matter what the matrix looks like. Why does this work? Start from the eigenvalue equation. A times x equals lambda x for some non-zero vector x. Now the idea. Pick the component of x with the largest absolute value. Call that component x sub I. It picks out row I of the equation. Row I reads, the sum of aij times xj over j equals lambda xi. Move the diagonal term to the left. That gives you lambda minus aii times xi equals the sum over j not equal to I. Divide by xi and take absolute values. Every ratio xj over xi is at most 1 by our choice of I, so the sum is bounded by r sub I. And you are left with the absolute value of lambda minus aii less than or equal to r sub I. The eigenvalue lives inside the disk around aii. That's the whole proof. That proof sits on a page. Let me show you what it looks like as a matrix actually moves. D is a diagonal matrix. B is the off-diagonal perturbation. We blend them through A of t equals D plus t times B. At t equals 0, the matrix is purely D. Off-diagonal contribution is 0. Each disk collapses to a point, and each eigenvalue sits exactly on a diagonal entry. As t grows, the disks bloom around the diagonal entries. Watch the two eigenvalues sitting at -1. They collide and then escape into the complex plane as a conjugate pair. They keep drifting as the perturbation grows. But watch, none of the eigenvalues, complex or real, ever leaves the union of disks. The cage adjusts with them. The cage adjusts, but it always holds. That's what every eigenvalue means. So where does this matter beyond the picture itself? Consider the problem of solving A times x equals b, where A is a huge sparse matrix, maybe 1,000,000 rows. Direct inversion is expensive, often impossible in practice. The standard move is Jacobi iteration. Split A into its diagonal part D and everything else, the off-diagonal remainder R. Rewrite A times x equals b as d plus r times x equals b. Move r times x to the other side, d times x equals b minus r times x. Multiply by d inverse, and you get a fixed point equation, x equals d inverse of b minus rx. Now iterate. Given a current guess x sub k, the next guess is d inverse of b minus r times x sub k. Simple. Cheap per step. But does it converge? Whether it converges hinges on one quantity. Look at the matrix d inverse times r. Call this the iteration matrix. Jacobi converges, for every starting guess, exactly when every eigenvalue of d inverse r lies strictly inside the unit circle of the complex plane. One eigenvalue touching the boundary or spilling outside is enough to kill the method. That is the whole condition. So, when is every eigenvalue of d inverse r inside the unit circle? Gershgorin answers that for free, the moment the matrix A is strictly diagonally dominant. Dominance just means that in every row, the absolute value of the diagonal entry is strictly larger than the sum of the absolute values of the other entries. Now look at d inverse r. Its diagonal is 0. Every off-diagonal entry got divided by the diagonal it came from, which was large. So when you draw the Gershgorin disks of d inverse r, each one is centered at 0 with radius strictly less than 1. Every disk sits inside the unit circle. So does every eigenvalue, and Jacobi converges. To see that actually working, I built two 4x4 matrices. The one on the left is strictly diagonally dominant by a wide margin. the one on the right fails dominance in a single row. I run Jacobi on both and watch the residual, the distance between the current guess and the true solution. On the left, the residual collapses. Each step cuts it by a constant factor. On the right, the residual grows. Each step pushes the guess further from the answer. The only thing separating the two outcomes is whether the Gershgorin disks of D inverse R sit inside the unit circle. Nothing else. Before the cage starts to feel like magic, 3 honest limits. The disks are sufficient, not tight. Real eigenvalues often cluster well inside them, and sometimes the disks look huge while the true spectrum is small. Strict diagonal dominance guarantees Jacobi converges, but it is not required. Plenty of matrices converge without it. And sharper cages exist. Brouwer's ovals of Cassini tighten the bound using pairs of rows. Similarity transforms can shrink the disks further. All of that lives one layer past this video. What you just saw is quiet, but it is everywhere. Every iterative solver in numerical linear algebra, every time someone asks whether an algorithm converges, there is a Gershgorin cage in the background, asking whether the right eigenvalues sit inside a unit circle. Once you see the cage, you read matrices differently.